Hello students, you're welcome to chapter 3 part 3 of network essential, okay, network essential management. Today we're going to look at fiber attenuation and dispersion. Okay, without much ado, let's begin. Introduction. The first part is to look at the introductory part of this chapter. Here, transmission is being limited by two factors. In computer networks, data that is transmitted is limited by two factors. These are called distance limiting parameters. Now, these two distance limiting parameters in optical fiber transmission, they are what? 1. Attenuation. 2. Dispersion. These are two distance limiting parameters in optical fiber transmission. So whenever we are transmitting data through optical fiber means, there are two things that excuse me, there are two things that will slow down this data that is being transmitted through optical fiber. One is attenuation and the second one is dispersion. Dispersion, like we said in the previous class, we say is pulse broadening of pulse, electrical pulse. So let's go and look at one after the other. Let's take a look at them one after the other. The first one is attenuation. What is attenuation? We've also spoken about attenuation in way back in chapter 2. So attenuation, it's just the loss of power that is being transmitted across the optical fiber cable. Okay, so we say attenuation is the loss of power that is introduced into fiber. Okay, so this loss accumulates as the light is propagated through the fiber strand. It's getting bigger, and the longer it goes, this loss gets bigger, because as it moves through the optical fiber, this loss gets bigger. So the more the distance that the light is propagated through, the more the loss that is taking place. So that's why we rate our channel capacity or the strand capacity based on the decibel per kilometer. Okay, decibel per kilometer. The loss are usually expressed in decibel per kilometer. Is that okay? The loss in lights that propagate through optical fiber, they are expressed in decibel per kilometer. That's the unit, decibel per kilometer. Okay, now the loss, or what you call attenuation, of the signal is due to what? The combination of four factors. There are four factors that are responsible for your signal degrading. So your signal keep degrading, keep getting lost. The strength keep getting reduced. So there are four factors that are responsible for the reduction of the strength of your signal. Remember, this reduction of strength of signal is what we call attenuation. So we are indirectly saying there are four factors that are responsible for attenuation in signals that are being transmitted or propagated in optical fiber. The first one is called SCA3. SCA3 is the number one factor responsible for loss of signal. The second one is absorption. The third one is microbending, and the fourth one is macrobending. Now let's take a look at them one after the other. Now the first one is SCA3. SCA3 is number one attenuation factors that limit how far a signal can go in optical fiber. So it is the primary loss factor. It's the main one. In fact, it amounts to about 85% of the entire loss in the signal that is propagated in an optical fiber. So it's a huge thing. So it's the main factor of all of them. Okay, over 3 wavelength ranges used in telecommunication today. So it's accounts for about 85% of the entire loss, right? The SCA3, it's also known as relief SCA3. You've studied this in physics, relief SCA3, and it's caused by refractive index fluctuations. The fluctuation resulting from refractive index variation in your wave causes this SCA3. Is that okay? Relief SCA3 decreases as the wavelength increases. So this SCA3 will reduce the more you increase the wavelength. Is that okay? So that's the first factor responsible for attenuation in signal that is propagated through an optical fiber. Now the second one is absorption. What is absorption? Absorption is the second loss, right? The second loss factor that is found in the signal or power that's propagated or transmitted through an optical fiber, right? Now, it is a composite of light interaction with the atomic structure of the glass. This absorption, it comes about as a result of the light itself. You know, you are propagating light across the core part of the optical fiber. Now, this core part of the optical fiber, this light interacts with the glass, the nomenclature, the nature of the material, the glass material that was used in making the core and the clady part of the optical fiber. So there is a kind of atomic interaction between the constituent, the makeup of the glass, and the light that is passing through. That results to a kind of energy, which is called the heat energy. So it involves the conversion of your optical power or your optical light to heat. It will result to heat energy. That heat energy is a loss. Remember, in the electrical or in the computer, once heat is generated, it's a loss. It's I square arrow. You know, it's called power loss. Power loss in electrical engineering. So it's a loss. So once your energy, your light energy is converted to heat, it becomes a loss. Okay, so this loss in this case is in form of a concept called absorption. One portion of the absorption loss is due to the presence of OH in chemistry now, OH ions, the OH ion, hydroxyl ions, okay, dissolve in the glass, the OH ion that are being dissolved in the glass during the manufacturing process. So, you know, when we are manufacturing glasses, we used to dissolve OH ion with other constituent components that are actually used for making the glass. So because the light come in contact and begin to have some characteristic reaction between the OH ions that are found, the negative ions that are found in the glass, and the light interact together, then a loss result, a heat loss result. This is one of the factors resulting to this heat loss, which is called absorption. This causes the water attenuation. It causes water attenuation or the OH peak. Now, let's take a look at that from the diagrammatical point of view. Now, you see, what you have here in this figure is a multi-mode system. You have a multi-mode here, you have a multi-mode and single mode here, and these are the nanometer, the distance through which the power or the strength of the signal can go. This is the wavelength for a specific, in nanometer, 850 nanometer for this optical fiber, but this is not mostly used anyway. We have 1300. This is the one that we installed in the 1980s and in the early part of 1990. But the 1550 is the one currently being installed or upgraded this to this. Okay, these are the wavelength in nanometers. These are the wavelength of the optical fiber in nanometer. Now, when plotted against the attenuation in decibel per kilometer, you can see that as the wavelength increases, the attenuation decreases. You can see from the graph, you can see the attenuation is decreasing. It's coming down. The value is coming down. The attenuation is decreasing as the wavelength is increasing, right? The attenuation is decreasing. Now, this is a single mode for a single mode case, okay? Because single mode, you need a bigger wavelength, right? So you can see. Now, what happens here? These two peaks, you can see there is a peak created here, like a sinusoidal wave, like a wave, okay, half wave. And also here, we call it the OH peak. So this one is causing instead of the signal to go like this, to go straight like this, to go like this, the signal, you can see the signal has to be delayed, lost will occur to it, because it's caused by the interaction between the light and the OH ions that are found in the genetic makeup of the glass, in the composite makeup of the glass. Remember, in the manufacture of the glass, there is OH ion that are dissolved with other substances that we use, silicon dioxide, reactive with boron, reactive with other elements that we are using. These are things that we are using making the glass, right? So we already know that from chemistry or from biochemistry. So when we have that, we react. When you see this signal as it propagates, it reacts here with the light reacts with the OH ion, so thereby causing a loss, causing an attenuation, causing a loss and attenuation in the signal, causing an attenuation in the signal. Are you with me? So this is what is happening in both cases, whether for this single multi-mode or for this single mode case. Okay, so this is what is happening. Attenuation, generally attenuation is decreasing as the wavelength increases. Attenuation decreases as the wavelength increases. But here is a single mode fiber. You see this SM, single mode fiber. Here MM is multi-mode fiber. So for multi-mode fiber, they usually have smaller wavelength. Single mode, the correct ones, they're using about between 1310 to 1550 wavelength, nanometer wavelength. Okay, so this is what is happening. So this two peak, this OH is causing a loss, attenuation loss, and this attenuation loss is described as scattering. Described as scattering. So the first factor limiting or causing attenuation is scattering, and this scattering is as a result of the light pulse reacting with the OH composition of the glass glass, and thereby causing signal degradation, reducing the strength of the signal. Is that okay? Thank you very much. So now let's move on to the next phase. Resulting to absorption loss. Okay, this is for absorption loss. Resulting to absorption loss. Now let's go to the third one, which is called the microbending loss. The microbending loss, the loss is caused by light mode breaking up and escaping into the clady. So you know light travels in the core. I have in the chapter 3 part 2, we showed you an optical fiber. We show you the core, the clady part, and the protective part. Now the light is traveling in the core, but sometimes because of bendy, because the cables are bent, sometimes there is a little break. So you see the light escape from the core that is supposed to move through, and it start going to the clady. It start escaping to the clady. So the loss caused by light mode breaking up and escaping to the clady as a clady part of the glass instead of the core, when the fiber bends, becomes too tight. When you bend the fiber and it's too tight, the light escape from the core to the clady. That result to loss. The light that was supposed to go to a destination, which is the detector part, the light escapes. Some of them escape to the clady part. Now such loss are described as microbending loss. Now as the wavelength increases, in this case the loss also in the bend also increases. You make the wavelength bigger, the more the loss. For this case, the wavelength bigger, the loss increases as well. Although losses are in just a fraction in decibel, they are small values, but the bed radius in small slicey trays and patchy enclosure should be minimal. Okay, should be minimal, so that it will not, if it becomes too significant, there you begin to ask yourself, what is the purpose of optical fiber if we can have so much loss? Okay, then number 4 factor that is limiting the signal propagation in optical fiber or that is causing attenuation is called microbending. You know, we have macrobending and microbending. Now microbending, this type of loss is caused by mechanical stress. You know, sometimes we stretch the wire, the cable too much, or we tighten it at both ends too much because we don't want laggy. Sometimes there we don't know that we overstress it. So this kind of mechanical stress placed on the fiber strand, usually in terms of deformation resulting from too much pressure applied to the cable. So when this type of stress is applied to a cable, the loss will definitely occur. For example, excessively tight wrap or clamp will contribute to this type of loss. So this loss is noted also in fraction of decibel. So mechanical loss that is caused by mechanical stress at the end of the cable, tightening the cable to ensure that they are super tight, sometimes result to mechanical stress, and this mechanical stress they contribute to what we call the macro bending losses. So these are 4 losses that are contributed to attenuation, that are resulting to attenuation. Now, we say there are 2 distance limiting factors in transmission, in optical fiber transmission. The first one was attenuation. The second one is dispersion. Now let's go to dispersion. Since we've looked at attenuation, the meaning, and the 4 factors that are causing attenuation in signal transmission in optical fiber, hence let's take a look at dispersion. Now dispersion, what is dispersion? Dispersion is simply pulse broadly. You're widening the pulse. The length of this pulse is getting wider. So that phenomenon, it's called dispersion in this regard. So pulse broadly is the second of the 2 key distance limiting parameters in fiber optical transmission system, right? Is the second key factor that limits how far a signal can be transmitted in an optical fiber. Okay, so since we've talked about attenuation, the second one that also inhibits or affect or bring a drawback of a signal be transmitted over a range of certain level in optical fiber, it's called dispersion. Okay, now since we've noted the meaning, it's also a phenomenon in which the light pulse spread out in time as it propagates along the fiber strands. The light pulse spreads out. Is the same thing that we've just said. Okay, let's take a look at this. This is a pulse. Okay, this is a pulse. This is the pulse, maybe from the input segment of it. Now at the output, this is what you get. You can see the width of this pulse. It's small, and then you see the width of this is bigger than the width of this. This pulse has widened. So this effect is called the dispersion. It's called dispersion. Look at this pulse. Now look at what happens to it. This is the input of it. This in a multimode. This is a multimode. Okay, look at the input. Look at the output. At the output, you can see each of the wavelength of this pulse is bigger now here. It's bigger here. So this one is called pulse broadly, dispersion. Pulse broadly. The pulse has been broadened. In this case, this one will result to error bit. This one will result. Dispersion always result to error bit. So we're going to look at that. Okay, we say this results in the broadly of the pulse. If the pulse broadens excessively, if it broadens too much, it can bleed into adjacent digital time slots and causes bit error. So there will be error in the bit. There will be error in the bit. And once there is error in the bit, meaning the digital signal that was at the input will not be exactly what will be received at the output. So if you say hello, hello might become something else. It will no longer be hello, hello, maybe it will be hello. So it will no longer be hello at the end. So there's bit error lost. There's something lost. So when there's too much broadly, when there's excessive broadly, there will be bit lost. But remember these bits, the 1010 in binaries or binary hexadecimals will be reconverted back to analog signal. So, but when they are reconverted, you cannot get back the original thing. So we must find a way to reduce dispersion, because dispersion will affect the entire signal that will be transmitted in the optical fiber system. So it will affect it. Dispersion and attenuation, there are 2 factors that limit how far our signal can go in the optical fiber system. Okay, so since we've talked about that, now let's take a look at the types of dispersion. We have 3 broad types of dispersion, 3 major ones. Okay, the first one is called the modal dispersion. The second one is called chromatic dispersion, and the third one is called polarization dispersion. Now let's take a look at them one after the other. Modal dispersion. Now in modal dispersion, this is caused by mode. Okay, this is when we transmit signal, pulse signal, in a multi-mode. When we are using a multi-mode, okay, we have the low order mode, the middle order mode, and the high order mode. So the dispersion that is caused by the presence of mode difference is called the modal dispersion. Let's take this one somewhere so that we don't cover our work. Okay, so modal dispersion, the broadening of the pulse due to different parts lengths. Due to the different part length, this one is taking, see this part length of this one is going straight for this low order mode. Now for this middle order mode, you just have to eternal reflection. Okay, then for this high order mode, totally eternal reflected, totally eternal reflected, you see this high order mode has a lot. So these are different modes. The dispersion caused by you see this dispersion, this one, the broadening of this entire pulse, is as a result of different mode of transmission. It's as a result of different mode of transmission. This type of dispersion that is caused by different mode lengths is called modal dispersion. It's called modal dispersion. The type of widening, broadening of this pulse that is caused by the use of different mode of transmission of light through this core is called modal dispersion. Are you with me? So modal dispersion occurs predominantly in multi-modes, usually in multi-modes, okay, like this type of example. This is a multi-mode, so it's usually from multi-mode. In this case, a light from a light source, the light rays can take many paths, right, as they propagate along the fiber. We've already explained that. Some light rays do travel in the straight one, like this one, like the single mode or the low order dispersion, and others take variable path lengths, routes, to reach where they are going. So at the end of the day, you see that the pulse width is wider, so the signal is wider, the width of the signal is wider, the pulse is bigger than the original one. So this dispersion caused by this difference in mode is called modal dispersion. It's called modal dispersion. So let's go on. I hope this is clear enough. Now let's go to the second one, which is called the chromatic dispersion. The chromatic dispersion. Chromatic dispersion is the broadening of the pulse due to the different propagation velocity of the spectral component of the light pulse. Okay, see, this is the pulse, right? At the input pulse. Okay, this is a refractive index profile. This is the refractive index pulse. This is a cross section of this case. Okay, now because of their different refractive index, you know, each of the ray of light have a different refractive index. The difference resulting from the refractive index in a single mode, or what you call the low order mode. Okay, in a single mode or low order mode, when different wavelength passes through and they reach at different time. You can see this one ends here, this one ends here, and this one ends here. The end of this, and the end of the last one, then it creates a pulse. It creates a length of the pulse, the width of the pulse. So comparing with the first input pulse, you see the output pulse is wider than this. This is caused by the refractive index, or the speed propagation velocity. This is caused by the propagation velocities. You know, the ratios of this their velocities is the refractive index. Okay, it can be defined as the refractive index, the speed of one over the speed of the other, or the light as it travel in one over the light as it travel in the other one. Okay, it becomes the refractive index. So in short form, in a simple way to explain this, we say the kind of broadly of a pulse that is due to different propagation velocities of the spectral components of the light pulse. Why we say spectra? Spectra means, when you say spectrum is singular, spectra is the plural. So when you say spectra, meaning you are talking about different rays of it. You are considering different rays of it. So the broadly pulse that is due to the propagation of velocity, the different speed. Velocity is the speed of the spectral component of the light pulses, and that when the pulse widening is caused by the difference in speed with which the spectral line of each of them travels, then such widening of pulse is called chromatic dispersion. It's called chromatic dispersion. Let's move on quickly. Now the third one is called polarization dispersion. The third one is called polarization. This one, where should we put this one here, right? The fourth one is called, and the third one is called polarization mode dispersion. Now, you know, polarization is just the orientation of your electrical flux, or your electric flux, with the magnetic field, electromagnetic field. So you have the x plane, you have the y plane, the orientation, reoriented them, electric field here, magnetic field here, and that effect of a wave is called polarization. That effect of a wave is called polarization. Now, so since we've talked about the meaning of polarization, now let's take a look at polarization mode dispersion. The broadly of a pulse, the widely of a pulse, you can see the output pulse here is wider than the input pulse here. Okay, these are their refractive index. Okay, the widening of a pulse due to the different propagation velocity of the x and y orientation. of the X and Y polarization component of the light pulse. You know, the light pulse has a horizontal component or horizontal orientation. It also have vertical orientation. So the light, as it propagates in the medium, the speed has the vertical orientation and horizontal orientation. So this vertical orientation of light and the horizontal orientation of light, both of them generally combine, create a pulse widening. So the widening of a pulse due to the propagation velocity of the X and Y polarization, the X arrangement and the Y arrangement of the speed. You know, the speed component has the horizontal component and the vertical component as it propagates through this mode, this optical fiber, this core part of the optical fiber. So as it travels through, there is a general electrical creating probably a 90-degree width or more than that with the horizontal component of the magnetic field effect of this system. So when that happens, we call polarization effect. That widening that is caused by the S component and the Y component of the speed of the light as it propagates through here is called polarization mode dispersion. Okay, so I hope this is clear enough. Now let's move on quickly to the next one. Now let's take this one here. I don't want us to block our work. Okay, now we have what we call the zero dispersion wavelength. The zero dispersion wavelength, meaning it is a zero case. Meaning there's no dispersion in the wavelength. Now there is a point where the dispersion is actually at zero. This be determined by the refractive index profile. So we have to check for every glass. We have to check, or every material, we have to check their refractive index. So this happens near around 1310 nanometer wavelength. Okay, and it's called the zero dispersion wavelength. So that's why, because of this research, excuse me, before now, because of this research, that's why we used to propagate at this wavelength. In the early 90s, we used to propagate at this wavelength in optical fiber. Okay, so because this is actually called the zero dispersion, because at this point 1300 nanometer wavelength, there is zero dispersion. There is no dispersion happening at this point. There's no dispersion happening at this point. So we call this zero dispersion wavelength. So at this wavelength is called zero dispersion wavelength. By altering the refractive index profile, then the zero dispersion wavelength can be shifted to another value, maybe the 1550. So what we did when we were bringing the new wavelength for optical fiber of 1550 nanometer, there we just play with the refractive index profile. So we change the characterization of the speed of light in the medium within itself. So we're able to arrive at a new zero dispersion wavelength, which is the better version of the 1310 nanometer wavelength. Now, such fibers are called the dispersion shifted, because you've shifted the dispersion away. This type of fiber that result the 1310 nanometer wavelength and the 1550 nanometer wavelength are called dispersion shifted. Now this is significant, is very important, because the 1500 nanometer region exhibits a low attenuation. Yeah, you see, you have zero dispersion, and then you also have very low attenuation. It's super beautiful, right? So it has low attenuation compared to the 1310. So that's why the option for 1550 is now gaining ground, because it gives a zero dispersion wavelength, and at the same time it has very low attenuation. So it's a huge advantage. This becomes an operational advantage. You see, the 1550 nanometer speed becomes an operational advantage, especially when we are transmitting through a long haul carriers. Since with minimum attenuations and minimal dispersion in the same wavelength region, repeaters and regenerator spaces can be maximized in this case. Now, the next phase, let's take a look at the water peak and the need for dispersion shifted fibers. Now, we've studied this diagram before. Okay, you know, we have water peaks caused by OH in the glass. Light interfere with the OH ion in the glass. So when that happens, we say there is attenuation, there's a loss. Because of this, then that's the super reason why super shifted fibers are very important. Okay, now let's move on quickly. Dispersion compensating fibers. Dispersion compensating fiber. A considerable amount of fiber in use today were installed like way back, like in the 80s and in the 90s, right? Now the cables were called the class 4A varieties of cable. Now these cables were optimized to operate in the 1310 nanometer wavelength region, which means that time they also had zero dispersion point, okay, for this wavelength. However, today we're trying to increase it to 1550 nanometer wavelength so that we can have a super low, not only dispersion is being reduced when you go to 1550, we will also have attenuation, low attenuation, which becomes a big advantage for us. Okay, so due to the continuous network expansion, because we have to keep expanding and keep researching and keep improving, in recent years it's often desirable to add a transmission capacity to the old fiber that we've already installed. This fiber of 1300 and 310 nanometer wavelength, we have to find a way to improve them, to increase the capacities of this old fiber to about 1550 nanometer wavelength region. Okay, especially since the attenuation at this 1500 nanometer is less than the attenuation at 1310 nanometer region. So you can see the reason why we are opting for a region of 1500 nanometer wavelength, because you both have a zero dispersion and at the same time a low attenuation, so your signal can propagate through a long distance and then we are good to go. One major problem still arises at this point. The dispersion value is higher at 1550 nanometer, which severely limits its distance capability. Okay, that is if you are not able to shift it correctly to arrive at zero dispersion. If you are not able to arrive at zero dispersion, then you will have a very high values of dispersion. Okay, so let's move on quickly. Dispersion compensating fiber. So because of that, we now try to create fiber that can compensate. By default, we want to compensate for dispersion. That means by itself it will reduce this dispersion. So to solve the problem we have, a fiber called the dispersion compensating fiber has been introduced. Okay, has been worked out, has been developed. This fiber acts like an equalizer. It acts like an equalizer. So what it does is that equalizer is something that if you say you are evil, maybe God raise up someone who is stronger like you that will deal with you. Okay, you're going to have a very strong opposing force. Okay, if you say you are strong, you find an opposing force. In my language, we used to say that omolorevie. So in my language, this is what we say. What it means is that if you in summary, if someone that is up to the task, when you meet, you bring a fight to someone that is up to the task, then there's no problem. Okay, so in other words, what we are saying, it's another word for equalizer. So what we are saying is that this optical fiber cable, we create a negative dispersion to cancel out the effect of the positive dispersion. That's all we did. That's why we call it dispersion compensating fiber. So dispersion occur, we create the negative pulse of it to cancel out the effect of the positive one. Is that okay? That's it. So dispersion is gone. You create positive, negative one, cancel it out. Okay, you create negative, positive one, cancels it out. So these kind of optical fibers are called dispersion capacity fibers. Okay, these fibers, they act like equalizer, like we said. A negative dispersion cancelling the positive dispersion. The fiber consists of small coil. Now, how do we create a negative aspect of it to cancel out the positive one? We use what we call small coil, normally placed in the equipment rack just prior to the optical receiver input. Okay, now this does introduce some axial loss of about 3 to 10 decibel, but which is okay, and may require the addition of an optical line amplifier. So we might put an amplifier because there is a little loss in the decibel, so that we can raise the value of the signal that we are sending in the first place, so that we can get the desired output. Okay, so now apart from dispersion capacitive fiber, we've also come with another method or another device called the fiber Bragg grating. Okay, the fiber Bragg grating is also introduced into optical fiber. This technology involves etching irregularity onto a short strand of fiber, which changes the index refraction. It changes the refractive index, or if you like, you say index refraction, and in turn reflects slower wavelength to the output before the faster ones. So it will reflect the wavelength before the wavelength itself will be reflected before the faster one gets there. This results in a compressed or narrower light pulse, minimizing intersymbol interference. Okay, so these two methods helps us to reduce or remove dispersion, the dispersion capacitive fiber and the fiber Bragg grating. Okay, so in this chapter, what we've looked at, we've used terminology such as scattering, absorption, microbending, dispersion, modal dispersion, chromatic dispersion, polarization mode dispersion. Okay, we have also used zero dispersion wavelength, dispersion capacitive fiber, and fiber Bragg grating. So this is all we have for this segment, chapter 3, part 3 of this network essential management. And thank you for attending our today's class. Once again, we say this is Waidsum University, the world's fastest growing digital and technological university. With us, you study virtual. You can be anywhere and everywhere in the world while you have your classes. Thank you very much for joining us today. Thank you.